Metals, have a look at the properties. First thing to understand, metals conduct heat and electricity. They're generally hard, mercury being an exception, it's a liquid. They're all solids, again, mercury being the exception. They're all dense compared to non-metals. They are ductile, which means they can be drawn out into wires. They're malleable, which means they can be shaped into different things. They're sonorous, which means they give a ring when they hit each other. A thing like that. And in general, they're shiny. Now, I know a lot of metals aren't, but that's because they're being oxidised on the surface. And all these properties are due to metallic bonding. Remember back to my board, to what we've gone through. Metallic bonding is a sea of delocalised electrons in a positive nuclei matrix. And if you can think of the electrons being like small ball bearings in between pieces of material, that these ball bearings will help and allow the material to slip and slide, to move. And that's what gives you the properties. Metal extraction. There's three ways that you start looking at metals. One, you can find metals native. These are things like gold, silver, sometimes copper. Right? You find them as the metal, not combined with anything else. You can find minerals. Now, mineral is a compound with the metal in it, but it's not necessarily got enough of the metal in it to make it worthwhile getting it. And then you have the ore. And ore is a mineral with enough of the metal present to make it worthwhile getting the metal out. Things like copper used to be about 8 or 9%. To have a copper ore with that in were worthwhile getting out. Now it's down to about 0.8. This is because a lot of copper has been used up. Extraction. If it's very unreactive, things like gold, you'll be able to find it as gold. So there's no extraction involved. There are rivers in Scotland you can go panning for gold and actually find it. If you've got a low reactivity, copper, mercury, then quite often you can just heat up the ore that contains the metal and it will fall apart, decompose, just leaving you with the metal. More often than not though, you need a chemical to be able to remove the oxygen, that's generally what it is, that's combined with the metal. And that chemical normally is carbon. So medium reactivity metals, things like zinc, carbon, iron, you heat up with carbon and the carbon will take away the oxygen, leaving you with the metal. For metals of very high reactivity, this won't work either. You need to use electricity in a process called electrolysis that we'll look at in a moment. This is why 200 years ago, the Emperor of France had a dinner service made out of aluminium, and it was the most expensive dinner service in the world at the time because aluminium was so difficult to get. As you can see here, if we heat iron oxide, this is the general ore for iron, with carbon, which is in the form in this case of carbon monoxide, this happens during the blast furnace, then we finish up releasing the iron from the iron oxide and forming carbon dioxide. This is known as a redox reaction. I'm coming across that in a bit. In electrolysis, a cell is set up as we can see here with a positive electrode and a negative electrode. In this case, the electrolyte is molten aluminium oxide. As this is an ionic compound, when it's molten, the two ions float around separately. The aluminium is a 3+ ion and will be therefore attracted to the negative base of the cell. The oxygen is a 2+ ion and will be attracted to the positive electrode, which is carbon, and so it joins with that and becomes carbon dioxide. This molten aluminium that's now at the bottom can be tapped off and we've made pure aluminium from aluminium oxide. This requires a lot of energy. We have here the reactivity series. As you can see on the left, tells you what's needed to extract them. So potassium, sodium, calcium, magnesium, aluminium, all need electrolysis. Zinc, iron, tin, lead, heating with carbon to extract. And copper, silver, zinc, copper, silver, gold, and platinum. I just couldn't fit it on. You generally find them native or just heating it. On the right hand side is the reactions. You've all seen it sometimes: potassium, sodium, calcium, lithium reacting with water. Magnesium will also react with water, but it's got to be in the presence of steam to be able to do it. As well as reacting with water, those metals will also react with a dilute acid, but so will zinc, iron, tin, and lead. Well, this is where you can order these metals, put them in reactivity order. When we get down to the bottom, you'll find that all the ones above will also react with oxygen, but copper and silver will also react with oxygen, and very slowly. Gold won't. Okay. And a detailed version of this that we're talking about in a few minutes, in the next bit of the topic, is found on page 10 of the data book, and it's called the electrochemical series, and that's what we're going to be looking at now. What is meant by displacement is that the metal that is higher in the electrochemical series, the more reactive metal, which is on page 10 of the data book, will kick out, displace the metal lower in a compound. So here we've got magnesium. If we put magnesium in a solution of copper sulfate, we'd see the copper sulfate, which is blue, would slowly turn to being slightly green, and would be magnesium sulfate. And the piece of magnesium that we put in would slowly turn to being copper. What is actually happening? The copper that's in solution is coming out to form copper atoms, and the magnesium that's not in solution to start with is going into solution. Remember, when an ionic solution is dissolved in a liquid, it separates and floats around as ions. So the copper is not floating around as copper sulfate, but it's floating around as copper 2+ ions, and the sulfate is sulfate 2- ions. And what happens is there's a change between the copper and the magnesium. What is happening is the magnesium is giving up 2 electrons. So it's going from a magnesium atom to being a magnesium ion, so it will dissolve in the liquid. Those 2 electrons are being picked up by the copper ion, and turning from being a copper ion into a copper atom. These are called ion half equations, and they can be put together. As long as the electrons balance, we should be able to cancel them out, and we're left with an equation This is an ion equation. You always have to remember though that the metal higher in the electrochemical series is donating electrons to the metal lower in the electrochemical series. What this gives us is what's called oxidation and reduction. Right? A new definition for oxidation used to be that some were oxidised if it reacted with oxygen. Now what we're saying is oxidation can be classed as the loss of electrons. Reduction can therefore be classed as the gain of electrons. And oxidation and reduction almost always go together to give us what's called reduction-oxidation equations. The easiest way to remember it is oil rig. Oxidation is loss, reduction is gain, and that's of electrons. So we're coming to the end of this little bit, and we've got magnesium. We've just looked and we can see the magnesium, which is going to donate electrons, that's oxidation as a equation. But the magnesium itself is making the copper reduce. So therefore the magnesium, even though it's being oxidized, is a reducing agent. It's making something else reduce. And the same goes the other way. The copper is being reduced. Okay? Well, the copper, let's say, is making the magnesium oxidize. So therefore the copper is an oxidizing agent. Sounds weird? If you're doing higher chemistry next year, you'll come across it again and again and again. Okay? If you look at page 10 of the electrochemical series in the data book, you'll find that all the equations that's there for all the elements that you're going to come across are all written for reduction. If you're asked for one for oxidation, then you write it in exactly the same form it is there, but starting at the right hand side. So rather than, as we've got for copper there, copper ion picking up 2 electrons to become a copper atom, you would write it the other way around. A copper atom losing 2 electrons to become a copper ion. Thing to worry about with that, the thing to think about with that is that non-metal ions, if you remember, gain electrons. So when you're looking at things for non-metal ions, they're going to be losing electrons to become atoms rather than gaining. We have here a simple cell. We made it with copper, magnesium, 2 different metals, and an electrolyte, which is an ionic solution. In this case, I just used common table salt, NaCl. Remember, the Na is going to float around as Na plus ions. The Cl is going to float around as Cl minus ions. Remember back to the video on displacement. The metal higher in the electrochemical series will donate electrons to the metal lower. Now, because we've got the electrolyte there, it means that we now have a complete circuit. The charges in the electrolyte can move, i.e. the ions. That means the electrons can move through the wire for the magnesium to pass them to the copper. This means that we get a build-up of a negative charge on the copper and a build-up of a positive charge on the magnesium. This will mean that the negative chlorine ions will be attracted to the positive magnesium. So they will come here, transferring over their electron to keep the circuit going. Whereas the sodium, which is electron short, will come to the copper, which is electron positive, lots of electrons, to pick up electrons. So we now have a complete circuit. That is the basis of all batteries and all electricity generation by chemical means. This is a simple cell. You need to remember that electrons carry the charge in wires, ions carry the charge in the electrolyte. In a more complex half-cell battery, we have what's called a salt bridge. This salt bridge, or ion bridge, completes the circuit. It allows the charges to move between the 2 half cells. The reason for using half cells is you can keep the electrodes in their own electrolyte, and so the battery will last longer. But the reason for the ion bridge or salt bridge is to allow the charges to move and to complete the circuit. And one last thing. In a cell, the bigger the difference between the 2 metals, the bigger the voltage produced. So you'd look in the electrochemical series, page 10 of your data book, and see which 2 metals gave the biggest difference if you wanted the biggest voltage. Or if the question is asking for the smallest voltage, which 2 metals are closest together. And you've always got to remember that the metal that's higher in the electrochemical series will be donating the electrons to the metals lower. So you're not going to get copper donating electrons to magnesium, but you will get magnesium donating electrons to copper. But copper would donate electrons to silver because that's higher. Okay?